Okay, good morning. Thanks for coming. So, after last night. So today I'm going to continue and want to construct this vector field which gives the local triviality of the minor vibration. So remember we have the fibers are like this. And we construct a vector field transverse to the fibers. And yesterday we listed, I gave a list of 3 properties that this vector field needs to satisfy in order to have a complete vector field, which is transverse to the fibers and is tangent to the sphere. So the vector field W must satisfy. So one is that the real part is 0, so this is tangent to the sphere. 2, so this is to have complete vector field, and this is to project onto U, and U, remember, is U is the unit tangent vector field in the circle. This is U. Okay, so we need these properties. So in order to have them, Milnor proved the following lemma. So if epsilon 0, there exists a vector field W on such that W set is tangent to the spheres, and, well, minus B, and for each point well, we have this equation. Well, okay, this is, well, I'm going to write it first like Milnor did, is non-zero, and the absolute value of its argument is less than pi over 4. Okay? So So remember that yesterday, instead of writing W, I wrote V, and I was saying that Milner constructed a vector field B, and then he normalized to obtain W. So I'm going to do the normalization directly. So instead of writing here non-zero, I'm going to write with real part 1. Okay, so if it has real part 1, then it's non-zero. Just one thing, we need to have this product to be non-zero, because if it were 0, that means, well, so if it were 0, the real part of this would be 0, and that means that this vector is real orthogonal to this one. So and that means that this vector lies in this E theta, and also it lies in the sphere. So that means it's in the Milnor fiber, and we want something transverse to the fiber and not in the fiber. So that's why we need non-zero there. Okay, so we were saying that we have two cases. So the first one is when set and grad log f set are linearly independent over C. So of course, well, if set and grad log set f set are linearly independent over C, of course, these two also are, because these and these are in the same complex line. Okay. So, and as I was saying, if they are linearly independent over C, they also are over R. That means that these two vectors are not one real multiple of other. So that means that the normal subspaces does not coincide. So that means that, well, this is the normal vector to the sphere, and this is the normal vector to the tube. So in that case, the tube and the sphere, so the sphere of radius z is transverse to the tube in the big ball of radius f of z. And so let me call this, well, since it's a transverse intersection, it's a submanifold, so let me call it by the moment M. So the tangent space of M, of course, is the tangent space of this intersection with the tangent space of this, and its normal is orthogonal complement of the tangent space. So the normal at set of M, the normal space, well, is precisely the plane, the real plane generated by these two vectors. And what I was saying yesterday is that the tangent space to M, in this case, it cannot coincide with the tangent space of the fiber. Okay, because you see, this is a codimension 2 submanifold of Cn. This is also codimension 2 manifold of Cn, but they cannot coincide. Why? Because suppose they do. So you take a vector here. So that means, since it's in the fiber, it has to be orthogonal to this I grad log. So that means that I grad log should be in this plane. But then, if I grad log and these are in this plane, that means that this is the complex line generated by this, which we're assuming it was not the case. Okay, so this cannot happen. So then we can choose a vector, a tangent vector in the tangent space on M. So it will be tangent to the sphere. Since it's in the tube, this will be 0, so it's satisfied. So just we need to take care of this last condition. So what Milnor did is, well, he asked for this condition, and what he did is he took these two equations, okay, so he took a common solution of these two equations. So of course this implies that is tangent to the sphere. So this, and of course if it is 1, its real part is 1. So it satisfies what the lemma says, but also it satisfies that because the real part is 1 is what we need here, okay? So in this case, just taking the solution of this system of equations, we get the vector field that we need. Case 2, in this case what we have is that grad log f of z is lambda z. The argument of lambda is less than pi over 4. And so what do we have here? We have, let me make a drawing. So we have z, somewhere we have grad log f of z. Remember that is orthogonal I grad log z, f of z. Okay, so we are now assuming that z is in the complex line generated by this vector. So this is this plane. Okay. Well, here we will have Iz, and z is normal to the tangent space to the sphere. Okay, so so we need to take something in tangent to the sphere. So we do what Raimundo and Professor Oka were saying yesterday. You just project this I grad log to a tangent space of a sphere, which will be a multiple of Iz. Okay, and that will work. So what we take is the following. We take Wz is Iz, but I need to take an appropriate multiple in order to get conditions 2 and 3. So I need to divide by the real part of the conjugate of lambda times norm square. Okay, so since we are taking a multiple of Iz, and this is tangent to the sphere, so then condition 1 is satisfied. Then we need to check just the other two properties. So property 3, well, also I need to check that, well, it satisfies what the lemma says. But so we have W of z I grad log f of z is, well, this is Iz. Let me take here 1 over real part, and this is I grad log f of z. But, well, I can take this I, and this is minus I, and then becomes 1, 1. And then this grad log is lambda z. So at the end, what I have is lambda over lambda bar over this. So since lambda has argument less than pi over 4, also in absolute value, so also lambda bar, this is a real scalar, so it also satisfies this. So we get what the lemma says. And also, well, if I take the real part of this, cancels with this, and is 1, so I obtain this thing. And since the real part is 1, well, so I'm getting 3. So property 3 is OK. And for property 2, we just need to look that the real part of W of Z grad log f of Z is the imaginary part of W of Z I grad log f of Z. Okay? So then what do we have here? We have that this number is, well, it has argument less than pi over 4, so it's in this region. It has real part 1, so it is here. So then its imaginary part has absolute value less than 1. So it does its property 2. Okay? So in this way, we get the vector field we need for the local triviality of. So now we have the vibration on the sphere. Okay, so now I want to see the vibration on the tube. So I just want to give the idea of this Tom AF condition and how we get a vibration in the tube using Ereshman vibration theorem. Okay, so Tom AF property. So, well, so I'm going just to try to explain it in the specific case we need. So take, as we have been doing, a map like this. So what we have is, again, well, the drawing won't be, so this is V, and remember, if we don't ask isolated critical point, since it's holomorphic, it has isolated critical value. Okay, so all the critical points are in B, and so we can take. So remember, we are in some neighborhood U of Cn, so we can take Whitney stratification of U such that V is union of a strata. So the picture here is not very nice, but here's B has some, well, different strata. But in the case of singular point, but it's just there are two, the point and the complement. But suppose that there are different strata there. So, and then, well, U minus B will be a big stratum. So what we do is take a stratum containing B, okay, and let me call S beta the big stratum. So take X in S alpha, take a sequence, well, let me call them set because they are complex things, in S beta, such that X set n converges to set. And what we do is take, let's call Fn, this will be, well, this Fn will be, so what I'm doing is here. I have set, and I have here some sequence converging to this. Of course, one important thing is set alpha is contained in the closure. So this, in the closure of the big stratum. So this Fn is just the fiber which passes through these points. Okay? So I could, so in general is you take this thing, it will be take the value of the function of Fn, and then take the inverse image of this, but restricting to your, so this is the fiber on the stratum, okay? And then, so then you will have a sequence of these fibers. Then what you take is the tangent spaces to the fibers. So you take T set n Fn and call T the limit. So maybe you need to take some subsequence to have the convergence. So these are like planes in some Grassmannian, which is compact, so you can do it. And so this Tom AF property is satisfied if the tangent space of set to S alpha is contained in this T. So in other words, what you're doing is you're taking the tangent spaces to the fibers, and then you arrive to some space T, and this will, if it contains the tangent space at C of the small stratum, then it satisfies Tom AF property. So you see, that's why asking for this condition, you get what Pepe was asking to have. So then now you take a small disk, and then you take the tube, okay, and when we take our sphere, and Pepe asked that the sphere is transverse to all the strata on the stratification. Remember, and we could ask that because of this conical structure. So what I'm saying is the singular fiber is already transverse, okay? And since the limit of this tangent spaces to the fibers contain the tangent space to the singular fiber, so that means that the nearby fibers are also transverse. So in that way, asking for this condition, you guarantee that all the fibers in the tube, in a small tube, are transverse to the sphere. So that's, well, so basically that's the idea of Tom AF property and why that implies the transversality of the fibers with the sphere. So then if we have Tom AF property and we have this transversality, that means that if I take a point here in this part of this boundary of the tube in the sphere, and I restrict my map F to the sphere, this point will be a regular point, okay? Because of this transversality. And so what I'm saying is, if I consider a tube, okay, and then, well, I restrict well, I'm going to do it just to the boundary of the tube. I mean, we are interested in the not in solid tube, but so take this restriction. So we know that so this part of the tube, if I take a point here inside the ball, since it's not in B, this is a regular point. Okay, so what I'm saying is F restricted to the interior of because this tube is a manifold with boundary, no? It's this tube and the boundary are this, well, in the picture, these two circles. So interior then is a submersion. And if I restrict also to the boundary, since if I ask Tom Mayer's property, these are transverse, it's also a submersion. Okay. Then what I have is that the restriction to the interior is transverse to this circle, and also the restriction to the boundary, to the sphere. Sorry, so let me say it like this. To the interior of the ball and the sphere, yes. So, no, sorry, yes, this is not wrong. So I restrict to the interior of the ball and to the sphere. So what I have is, so in the interior of the ball, of course, the points in B don't go to the circle. So what I mean is this restriction is transverse to this circle. And from this transversality in the tube, the restriction to the sphere also will be transverse to the circle, okay? So by differential topology, what we have is, if we have a manifold with boundary, which is a map from a manifold with boundary to a manifold without boundary, well, in fact, here will be C, and we have here a submanifold, and this, the restriction to interior is transverse to the submanifold, and the restriction to the boundary is also transverse to the submanifold. What we have is that the inverse image, well, sorry, it's like this. The inverse image of the submanifold, which is precisely the Milnor tube, is a manifold with boundary, okay? So in order to have this nice tube as a manifold with boundary, of course we need this transversality. But then also the same thing is, what we have is, now if we restrict to the tube, what do we have? We have, well, this is compact, so this will be proper, is a surjection, and then if we restrict to the interior of the tube, is a submersion, and if we restrict to the boundary of the tube, is also a submersion. So these are the conditions for Ehresmann fibration theorem to work in manifolds with boundary. So let me state it. So what we have is, we have a map from M to N. So this is with boundary. This is closed. So see, F is proper surjection, and F restricted to the interior of M submersion, and F restricted to the boundary, also submersion. Then F is locally trivial vibration. Okay? So then this is how we get this vibration in the tube. But the good news is that all holomorphic maps satisfy this condition. So we have always this transversality, and we have always the vibration on the tube. So, okay, so this fact is what, when Milnor wrote his book, he didn't know. Then Hironaka proved that all these maps have this property, and this is what Le used to prove the vibration on the tube. That's why we call it Milnor-Le vibration. And okay, so now what we want to do is see that the vibration on the tube and the vibration on the sphere are equivalent. So as Pepe mentioned, what we need is a vector field to inflate the tube into the sphere. So let me do that. Are there any questions about the vibration on the tube? No? Okay. So let me make the drawing again. Okay, so what we need is just a vector field in the ball minus B, so such that it's transverse to all the spheres and transverse to all the tubes. And remember that we want that if we take a integral curve of the vector field, the argument of the image under F is constant. So that means that this integral curve will lie completely in some E theta. So, and this will be the argument. Okay, so let me write. So we need a vector field V here such that so it is transverse to all spheres where B, it is transverse to all tubes, and C, as I said, if it is an integral curve of B, then F of B T has constant argument. Okay. So how do we construct this? Well, again, Milnor uses what I call yesterday the key lemma, and the construction is very similar to the previous vector field. So he constructs this. So again, we take epsilon less or equal than epsilon naught. So there exists a vector field B here is such that is real and positive for all set here, and this inner product has, well, let me put it like this. So the real part is positive. Okay, so we will see that with these conditions, we get a vector field satisfying A, B, and C, and we will see how to construct this. So again, we have two cases, which are the same as before. So set and graph log f set are linearly independent over C. Okay. So in this case, what we take is the following system of equations. So it's B graph log f set equal 1, and B set some complex number k with real part bigger than 0. Okay, so, and, okay, so of course, this, well, if this one is real and positive, and I'm asking the second condition. So, and case 2, what we do is, well, this case again is graph log f of set is lambda set with argument of lambda this pi over 4, and in this case we take b of set equal to graph log f of set itself. Okay, so in this case, yes. So take, so it's grad log f of set. So I need to see this. But this is a lambda set. And this is, okay, so it's real and positive. And then well, this is lambda set. But again, this, well, of course, this is a real number, so the argument does not change. And the same thing, we are in this region, so the real part must be positive. Okay? Okay, so now we get the vector field, which the lemma tells us, but why this implies the properties there. So here is this. Okay, well, pues recall that if we take d log set dt, this was the real part of the derivative of the log of f. So this is real part of, well, let me put here along a curve. So this is the real part of the p dt of grad log f of z. But this is, well, some c bigger than 0, okay, because if it's real and positive, the real part is positive. And so what we get is that log fpt is precisely ct plus some constant d. Okay, so fpt. Okay, so then this is well, when t grows, this grows, so that means is transverse to all the tubes. So this is the second condition. Then we can do the same for theta, because remember d theta pt dt, it was just it was the real part of this with I, but this is the same thing as the imaginary part of dp dt grad log f of z. But this, I said it was real and positive, so this is 0. So then it's just some constant. So that means what we get condition C. And also, well, so we have that the real part of this, of course, is positive. So now what we take is the pdt squared dt, and this is 2 times the real part this, which is positive. This positive, so the derivative is positive, so that means this norm is always increasing, so that means it's transverse to all the spheres. So we get what we want. So just we do as Pepe mentioned, you take a point in the tube, and then you consider the integral line which passes through this point, and then you follow this integral curve until you hit the sphere, and that will give you the diffeomorphism. Okay, so basically, now another remark. So now we have this vector field, and what is this? Of course, it allows us to see that the vibrations on the tube and on the sphere are equivalent, but again, it's telling us something else, which is that, remember, this means that the curve is contained in E theta for some theta. So that means that since Pt is transverse to the spheres, that means that if we have this vector field defined in all the ball minus V, what we will have is, again, that all the spheres will be transverse to E theta. Okay, so this is again remember that this is what we call the irregularity. Okay, so once more, this classical proof of Milnor is saying that we should consider this, or in the complex case, we always have this. And also, remember that this also implied that phi, the vibration on the sphere, is a submersion. Actually, there is a if and only if this is a, so the map is irregular if and not, so that means this, if and only if this is a submersion, and also, well, if this is a submersion and this is irregular, we always can construct this vector field. So the three things are equivalent. And but you see, in the complex case, so we always have this, but we have this very powerful key lemma using this curve selection lemma to prove all these things. In the real case, we won't have that. We don't have this complex structure. So it will be true again that this Isusa summation will be equivalent to be irregular and will be equivalent to have a similar vector field, but the way to construct the vector field will be a bit different. Is what I'm going to try to say now. Okay, so now we go to the real case. Okay, so real case. So now, well, we're going to consider maps from Rn to Rp. Okay, so in order to have a vibration as before, but now it's over norm of f over some ball minus the link to the sphere. So we need, okay, so in the complex case, we just need to ask f holomorphic, and we have it. But in the real case, it's different. So we need to ask a different thing. So the first thing, well, to have something analogous to the complex case, the first thing we are going to ask is, of course, that 0 in C, well, in Rp, is an isolated critical value. Yeah? In the holomorphic case, we have that automatically, but in the real case, we don't have it, so we ask for it. Of course, we need Tom AF property. Well, if we ask this, as I mentioned, we guarantee that we have the vibration in the tube. As Pepe mentioned, this is a sufficient condition, so it can be weakened. In fact, so basically the condition is that the fibers are transverse to the sphere. So, and we would like to have a nice way that given a map to identify if that is the case. So then we have vibration on tube. Again, as Milnor did in his book, he constructed in the case of isolated critical point, he constructed a vector field which inflates the tube to the sphere, but his vector field doesn't have any. You don't have any control of the projection in that one. So in this case, using the same vector field, you can inflate this, but you will get a vibration in the sphere, but you don't know the projection. And we want the projection be as in the complex case. So for this, we ask the irregularity. Okay, so I will just give the idea how, if we ask the irregularity, we can construct the vector field analogous at the one I just constructed. And also, well, also this, remember, I will say how to construct the vector field, but also this implies that phi is submersion. Otherwise, we cannot expect that this to be a fiber bundle. Okay, so, and as I said, we need to ask for this so that we don't get them when we consider real. So in fact, we have examples of things where they have one property and they don't have the other. For instance, if we ask isolated critical point, so Milnor himself gave an example. So he considered this map is his famous example in page 99 of his book. Okay, so this, well, has isolated critical point. So as Pepe mentioned, just by implicit function theorem, you have vibration in the tube. So you don't need to ask for this. But this is not a submersion. In other words, this is not irregular. Okay, so we have examples of vibration in the tube, but they are not irregular. Example, this is Milnor's. An example by Jawad-Snoussi, which is the following. Well, let me put here R. So this has isolated critical value. V is just the z-axis and is deregular. Okay, but the interesting thing is when R equals 2, has no vibration on tube. And the reason is, so let me say, in both cases, so in general, has no Tom. It does not have Tom AF property. When R equals 2, well, it doesn't have vibration on the tube. But if R is 3, it has vibration on tube. You see, so this is an example that you don't have Tom AF, but still you have vibration because the fibers are transverse to the sphere. So you see, in the real case, basically everything can happen. So you need to start asking for some conditions in order to try to understand. So let me see what else. Okay. So the question is it easy to find examples which satisfy all the properties? Well, the answer is yes, and one family of nice examples are the called polar weighted homogeneous. Okay, so what are these? So if last week you went to Agustin's talk, he mentioned this family of maps. So 2n 0 R2 0. Okay. So F is all are weighted homogeneous if there is an action of R plus crosses 1 on Cn. So let me call this T lambda Z1 Zn will be P P1 lambda D1 Z1 T Pn lambda Dn Zn. So the Pi's and Di's are positive integers and greatest common divisor of 1 and of the Dn of Pn as well. And we have that F of T lambda Z1 Zn equals T lambda df for some P and D integers. Okay? So you see examples of these things. Well, first, complex weighted homogeneous polynomials. Okay, so remember when Pepe started his lecture, he was focusing in one example, it was a homogeneous polynomial. So, and of course, that homogeneous polynomial is a particular case of these complex weighted homogeneous polynomials. And remember that you had, well, this, the action of C star, when you restricted to R plus, you were getting the orbits of the action were like transverse to the spheres, so it played the role of this vector field to inflate the tube on the sphere. And when you restricted the action to the circle, you get these orbits which, play the role of the vector field which gives the local triviality. So these are not necessarily holomorphic maps, and using these actions as Pepe did, one can prove that you have, well, first of all, all these have isolated critical value, and you have vibration on the tube and vibration on the sphere. So yeah, and so everything is satisfied very nicely. More examples. Pepe mentioned some is this Fam-Briscorn, twisted Fam-Briscorn. Fam-Briscorn. What are of the form Z1 A1 Z sigma 1 bar plus Zn An Z sigma n bar. Sigma is a permutation and the symmetric group of n letters. So these were considered by Rua, Seade, and Berhovsky. And in fact, these have isolated critical point. And since of course, this Miller vibration, of course, is with projection this. So they are irregular. And the irregularity is given by the action of R plus. Okay. And also in this family, as Pepe mentioned in his last talk, there are very nice behaviors, new behaviors, compared with the complex case. He mentioned that work of Aide Aguilar, she looked in a particular family of these kind of maps, and she obtained new open book decompositions, no, that cannot appear in complex singularities. And also, here, as Agustin mentioned in his talk, there are also some strange things happen. Because in the case of complex weighted homogeneous maps, you can prove that they have to be polynomials. But in this case, you can have series. So strange things happen. So then I think just here, it would be interesting to learn, understand more this kind of polynomials, because we have all that properties almost for free because of the actions. Also, well, when do we have also Milnor fibrations? Professor Oka mentioned in his talk about this strong non-degeneracy condition, which implies to have Milnor fibration. What else? Okay, so let me now tell you, if you ask for all these properties, having the regularity, how do you get this vector field, which inflates the tube into the sphere? Okay, so, well, I just erased it, but it has Tom AF, and is the regular and isolated critical value. Okay, so what we do is, so let's do the drawing again. Okay, so now we want, well, this is RP, so I'm just drawing it as R2. So we want a vector field such that when we have the integral curves, when I compose the curve with f, they will be on array, because when we project into the sphere, it will be, we have constant value there. Okay, so since we have isolated critical value, of course, in the ball minus b, this is a submersion, and we can do as we originally thought in the vector field, which gave the locally trivial triviality, is take the radial, here take the radial vector field. Okay? Since it's a submersion, we can lift it. So we will get, what we will get? So we will get a vector field which is transverse to the tubes, okay? But we also need transversality with the spheres. So how do we get that? Well, so the trick is to use a map. I'm going to call, well, I'm going to note like this. And this is a map from, well, my neighborhood to minus b, to a p minus 0, and it's defined like this. Of x is like this. So you see, if I just write this, what I'm doing is just composing f with the projection to the sphere, as we did yesterday to prove that phi doesn't have critical points. But when I put in this, I change in the radius. So that means, but the first property of this is if you are in a sphere of radius, I don't know, whatever, epsilon, then the image will be a sphere of radius epsilon, because this has norm 1. Okay? So it sends spheres into the spheres. In other words, if you restrict to a sphere, you see it's like the map of the vibration on the sphere. So it sends the sphere minus the link to the sphere, but just scaling each time and putting all these like vibrations together. And since it sends spheres to the sphere, we call this the spherification of f. And a nice thing about this map is that, as I mentioned, we have a equivalence of deregularity with phi being submersion, but also with f submersion. So if the map is irregular, this spherification will be a submersion. And this is very nice, because then what we can do is take, again, the same radial vector field. This spherification map is a submersion. And of course, since it sends spheres to spheres, if I take a point here, the fiber will lie in the sphere. Okay? So if I lift this vector field using the spherification, I will get a vector field which is now transverse to the spheres. Okay? And then, well, it's simple. You have these two vector fields. You add them, and you get a new one, which has the two properties you want: transversality to the tubes and transversality to the spheres. Of course, one has to be careful, because what if, in some point, they are collinear and in opposite directions and they cancel? You don't want that. So you need to prove that that is not the case, that you always get something which is non-zero and have the properties you need. So this new thing was what we needed in this real context to, instead of this, well, complex thing that Milner used. So now, with this, you have, so deregularity implies this submersion, and then you can construct this vector field, and then you can inflate in a controlled way the tube to the sphere. So the vibration on the sphere will be f over the norm of f. Okay, so what else? Okay, so just, well, I think I will finish early. I want just to say one more thing. It's just, well, doing again what Pepe was saying, why we are interested in understand these real things. Well, because really we are getting new things, much more things that you can get with complex singularities. Because, for instance, he mentioned that if you have a holomorphic map from C2 to C, so the link So the link in this case is an iterated torus knot. Okay? So in this dimension is a very special class of knots you can get with complex singularities. But in the real case, Perron constructed a map such that the link is the figure egg knot. And this is not an iterated torus knot. As Pepe mentioned, there is a paper by Agbulut and King which says that actually every knot is algebraic. So in other words, you can find some polynomial such that the link realizes it. So then you see from very specific family of knots, then you can get every knot with the reals. And well, and this is in a very particular dimension. But then, so well, let me call this G just to illustrate. So now, a recent result by Aida Aguilar, she did the following. So she took G, let me call it G of x1, x2, x4, and then she took some complex variable and raised it to R. So she is like studying these sort of things. What she got is that the link of this thing is the R cyclic cover of S3 branched along the link of this, which is the figure 8. Okay? Well, it's the total space of this cover. And in three-dimensional topology, it's known that if R is greater than 3, this is an hyperbolic manifold. 3 manifold. And in complex singularities, you cannot never have hyperbolic manifolds as links. So here, again, in singularities, there is this nice interaction between topology and manifolds and the singularities. But now it's like, well, look for new interactions between singularities, and now we open the door to the hyperbolic world as well. So there are many nice results about the hyperbolic manifold, so it will be interesting what is the interaction with the real singularities. And what else? Okay, so one thing about this case, that when we have all these properties and we ask for isolated critical value, is that we are imposing all these conditions, and so the examples are not generic. So they are like particular families of maps. So you are asking many things to get what you need to make things work. So, but, well, collaboration with Nivaldo and Pepper, we recently proved a general vibration theorem. So you have maps, again, Rn, Rp. You don't ask anything, so the critical points can be as you want. So we get, again, a nice ball, closed ball. And this ball, we see it as a stratified space. So this is just the interior, and we get, so this is the biggest stratum, and the other stratum is just the boundary. And what we do is take the restriction to the interior and take the set of critical points, so called critical points of this. Of the restriction to the interior, call this, well, now again you get critical points, but now you restrict to the sphere, okay? And, well, called critical points of F, just the union of both. And so the discriminant is just the image of this. Okay? So what you have is so now the picture is, well, you have B, but the set of critical points can be, I don't know. So then you are here, and your discriminant can be, I don't know, some way. So then your target can be just, so the complement of the discriminant can be disconnects, okay? But so then we prove a general vibration theorem which says that if you take, so you consider some, okay, so we construct also some kind of Milnor tube, but what we do is, again, we take the inverse image of some boundary of some disk, but we remove any point in the discriminant. So we are taking out the pre-images of these bad points. And the theorem is that if we restrict to this tube, this is fiber bundle. Well, it's nice to have a vibration, but it's too general that it's difficult to say something about it. The first not nice thing is that, of course, depends strongly on epsilon, because since you are considering critical points restricted to the sphere, if you change the sphere, the critical points can change, because fibers that were transverse in one sphere cannot be transferred in the other. So that's not nice. Of course, in this generality with the critical points, you can say a bit more if you ask, again, Tom AF condition. You guarantee that in the small tube, you have transversality, so that in that way, then it essentially does not depend on epsilon, so it's a bit nicer. But also, so then what we did is we consider another map, G, which has isolated critical point with respect to some stratification of given by the first map. And then we could say something about we can say something about the Euler characteristic of the fiber of F in terms of the Euler characteristic of the fiber of G and some index of some of the gradient of some vector field, gradient vector field related with G. So, but And so so we were working this, and as usual, it's difficult to have examples. So the theory was nice, and then this was of the wonderful things to visit Sao Carlos. I was speaking with Cedinha. Cedinha told me, consider this finite determined maps of Corang 1, and you have some very nice generic properties in this case that give you all what you need. So we have a very nice family of examples which reflected our results. So you see, real singularities are more complex than the complex ones, but there are many interesting things. So now it's just a question of the different ways you can learn things about them. So, and with this, I finish. Thank you very much.